Good morning. My name is Peter Fankhauser. I'm a PhD student at the Robotic Systems Lab, ETH Zurich in Switzerland. In this presentation, I'd like to introduce you on how we have been using ROS in the ARGOS challenge with the robot ANYmal. The ARGOS challenge is all about a fully autonomous inspection of oil and gas sites. The robot needs to plan complete missions, take decisions on the fly, and navigate in tight and difficult environment. The goal is to reach and inspect several different elements on the site and report back to the operator about the state of the site. For example, here reading this pressure gauge. Our robot ANYmal uses front and back lasers, laser range sensors to localize and map the environment and to detect obstacles such as this chain. Because of its legs and thanks to its maneuverability, ANYmal can change its pose and get the camera to get a good view on hard-to-reach places. Here, reading out the status of the lever. The operator needs to be always able to see what the robot is currently doing and be informed about the next actions and, if necessary, take over. The accurate localization and mapping and motion execution that we have on ANYmal allow to reliably climb up and down steps. And when approaching an obstacle, ANYmal can change the configuration of its legs to climb over these obstacles without interacting with them. In case of this very steep industrial staircase, we made use of the high range of motion of ANYmal to safely crawl up with help of hooks on the belly. This enables the use of ANYmal for the inspection of multi-level sites. The ARGOS challenge is organized by the French company Total together with the French research foundation ANR. Their first competition was in 2015, the second one was this year, April, and the next one will be next March, so pretty soon. More information you'll find on the website of ARGOS. Now what's important, what's given to us in this challenge is a map of the environment where all the points that we need to inspect are marked, and we get a CAD model of the environment. The CAD model is somewhat accurate, but not very much, so we can use it, but it's sometimes difficult. And before a mission, you get a mission statement, like in this example, where it's written, okay, you have 45 minutes time, go and inspect these elements and report back. And then in a couple of minutes later, you need to start the robot and then not touching the computer at all. There are 5 international teams. And if you look at the teams on the left, all the other teams use tracked vehicles. They have flippers in the front and the back. They're all custom built for this challenge. And we're a little bit the underdog in this challenge with a robot, which is a little bit more complex, uses legs. We think that legs, we can be more versatile in the environment than with tracks, and we can cope with more difficult environments, for example, climbing over obstacles without touching. This is our team, Team Leo. This picture has been taken a week ago when we went climbing up in the beautiful Swiss mountains. And we are a team from the Robotic Systems Lab and the Autonomous Systems Lab. This is a robot ANYmal. It has a main body which hosts all the electronics, all the brains, all the PCs. We have aluminum thighs and carbon shanks, which makes them very lightweight. The battery, which lasts for an autonomy of roughly 3 hours, is housed in the belly of the robot. We have front and back Hokuyo laser range sensors for localization and mapping. We have contact sensors or force sensors in the feet for walking and trotting. There's a protection frame which makes it easy to carry the robot around, and in case it falls or collapses, it doesn't hurt itself. In this application, there's a modular plate that we can use for different applications. And here we use the pen tilt inspection head that hosts all the inspection equipment. Now, the special thing about this robot is the custom joint actuators that we built, called ANYdrive. These are fully integrated robot joints, which allow you to accurately do position control. These ANYdrives host a motor, a gear, and the spring and all the electronics that goes along with the motor. The spring, this series elastic actuator, allows us to do very accurate torque control. Our sensor are absolute position sensing, so once your robot is calibrated, you don't need to do that anymore. Our custom controller on board of the ANYdrive is programmable, so it's nice you can bring quite some intelligence into the joints. Because of the spring, the drive is impact robust, so far, even though if the robot jumps or drops, the gears won't break. It features a hollow shaft such that we can do nice cable routing of the feet, from the sensor feet through the whole entire leg, and the ANYdrive is waterproof. So this is what really enables our robot to do all these maneuvers. Now looking at the system, we have 3 PCs on board, and the first one is the locomotion PC, which communicates with the ANYdrive, the IMU, and the contact sensing we have. Internally, we have our custom real-time threading framework, which runs the state estimation and the real-time locomotion control and balancing control. It features a ROS interface, and then with ROS, we can communicate with all the other PCs, such as the navigation PC, which is communicates with the laser range sensor and wide-angle cameras for the operator. On this PC, we do localization, terrain mapping, motion planning, and mission execution. And all of this is held together by ROS and communicates over ROS also with the inspection PC, where all the inspection equipment is on board, where we do the visual inspection, thermal, and audio inspection. The robot carries a wireless router, which communicates through antennas on the site with the operator PC, which is somewhat remote and doesn't see the robot actually. There we run the remote control user interface, visualizations, and prepare the mission. For safety, we have on a different frequency a safety operator which can shut down the robot in case something goes wrong. Now I want to go through each of these PCs a little bit and show you how we have been using ROS. I'll start from the left to the right and start with the locomotion PC. This is the setup of how we do the real-time control, where we get the sensory input and use this in our state estimation, which then provides the state of the robot, which is used by the whole body controller to stabilize the robot. This then generates either joint position or joint torque commands, which are then translated and tracked in our ANYdrives, which are then eventually execute the motions on the robot. Now the state estimation is very important, as this allows us to do the balancing control and fuse all the localization with it. Here we use an extended Kalman filter, which takes no assumption on the terrain, so it doesn't need to be flat. And with the kinematics of the encoders, we can then create kinematic relationship from the feet tips to the base. And when we take the assumption that the feet, when they're in contact, don't slip, we can estimate the motion of the robot. We fuse this in the Kalman filter with the measurements from the IMU, and roughly when we measure over distance, depending on the calibration and the environment, we get an error of 1 to 5% over the distance. When we have external localization, such as be it GPS or localization from the laser, we can fuse this as well in our state estimation. Now, this software is based on open source software, and on the top right, I'm going to show all the open source software links to that. So keep note when this sign pops up that you can find the software under our GitHub account. Now going to the whole body control, the robot can do several gaits, such as trotting, crawling, and some special maneuvers, and all of this is based off our locomotion library, which hosts all these different elements for pose optimization and control. When running these different tasks, we need to switch in between what we have been building, and something that we want to open source soon is this library, the robot controller manager, which switches between the tasks safely, between these real-time tasks, and also has multiple emergency layers in case one of the tasks fails. It can recover with an emergency controller to do recovery maneuvers, or in worst case, trigger a fail-proof emergency controller to freeze the robot. One of the special things that we worked on is this library called FreeGate, which is also open source available. It's essentially an abstraction layer for whole body motions, what we call the FreeGate API, and allows us to do all these motions that you see in the video. It allows you to robustly execute motions in task space, so you can define motions for the base or the feet in different frames. And it's implemented as a raw section, which means we also provide frameworks for YAML files, Python scripts, or C++. In the example, what you see is a robot doing a 3-legged push-up, very easy, and the code on the left, essentially all you need to do this motion. So with only a couple of motions, you can quickly generate various motions for the robot. So it makes it also easy for unexperienced users to control the robot. Now you can imagine all this locomotion optimization steps. We're heavily involved with 3D rotations, and they're sometimes difficult to work with. So what we did is to open source our library called Kinder, a kinematics and dynamics library for robotics. It's a C++ library for the consistent handling of rotations. It supports rotation matrices, quaternions, etc. Importantly, also, of course, it can do all the common operations, and what's important for optimization, it also includes the time derivatives of these types. There's a ROS interface available. It's based on Eigen, it's very efficient, and it's fully unit tested. We also have a cheat sheet that goes along with it, explaining the concepts and showing how we derive certain entities. Now going on to navigation, essentially what we do is take the laser range data, which helps us to localize the robot, given the reference map that we get. Then together with the pose, we can create dense terrain maps of the environment, which we can then interpret as traversability maps on which we can do navigation planning and then finally execute the motions on the robot. Now, starting with localization, there's also an open source software from our laboratory. It's essentially scan matching iterative closest point, ICP, where we have given a reference point cloud and the robot can accurately localize within that map. What we do is aggregate point clouds from the rotation of the robot, from the rotation of the laser scanner on the robot, and then fuse those and localize within the given map. It either works with a given map, but you can also use it for online mapping. Within the ARGOS challenge, we were able to localize in sub-centimeter accuracy, which is very important for certain tasks that you need to do. Given the pose and the laser scans, what we can do is to create dense maps of the terrain. There's also open source software called elevation mapping, and it's about the probabilistic fusion of these range measurements together with the pose estimation. Because it's all probabilistic, we take the noise of the pose, the scanner, and also we can explicitly handle drift of the robot estimation. We have several types of noise models. We have been using it with lasers, Kinect, stereo cameras, Velodyne, etc. Now, when working with these elevation maps, we'd like to do various interpretations and calculation, etc. on them. So what we've been doing is to create a new format, what we call grid maps, which are essentially universal multi-layered 2.5D maps, which on the left you have all this data, create an elevation map, and then with this grid map library you can do all kinds of math with it. What we've been doing, it's implemented as a 2D circular buffer, which means when you move the map around, for example, when the map moves with the robot, you don't need to move any data in your memory. So it's very efficient. It's all based on Eigen, so we can take the power of Eigen, and here's an example where we quickly calculate the root mean squared error of the map in one line of code. There's a bunch of math functions included that we provide, and also iterators that allow you to do different calculations as shown in these examples. For example, circle, spirals, etc., and lines. Of course, it's fully compatible with ROS, and we have OpenCV interfaces as well. And so you can convert from to images, point clouds, occupancy grid cells, so it's fully compatible with the existing navigation stack. Also, we wrote a ARVIS visualizer to show the maps as these height maps in ARVIS. Now, given these height maps, what we want to do is check where can a robot actually walk and where not. What we've been doing, we have several filters to interpret the elevation map, such as checking for slope, roughness, and step height for each cell and for its surrounding cells. And getting that together, then we create a traversability map where the blue elements mean, okay, here it's easy for the robot to walk, and red means the robot cannot go there. Also, this software is available open source. Now, when we have the traversability map, we can do motion planning on it. And here you see an example how it works without a map, but we can also initialize it with a given map. And this is based on RT star from the OMPL library. The nice thing about this, we do continuous local and global replanning such that it can cope with a changing environment and update as necessary. Inspection. One of the big parts is the visual inspection, where we have to automatically read pressure and level gauges and valves. So what we do here, we have a zoom camera on board and then use computer vision to read out the state of these elements. Other inspection elements include thermal inspection, where we have a thermal camera on board to read the temperature of certain hotspots. And also auditive inspection, where we need to measure if the pump operates in the normal range, if there's any gas leaks around in the ultrasonic range, and we constantly need to listen to platform alarms. If the sound occurs, then the robot needs to recover to a safety area. And here we use microphones to do this Fourier transformation and analysis. Now in the following, I'd like to go a little bit into one example on how we automatically read these pressure gauges. So first we need to know from which viewpoint can we actually look at the pressure gauge. And here we've been writing a piece of software that automatically checks available position and measures how robustly can I see it from this position. Now when this position is given, the robot needs to actually go there and then use its pose and figure out how can I move the camera such that I have a good viewpoint, because sometimes these gauges are really high up or down low. When the gauge is in the viewpoint, then we use visual surveying to accurately zoom onto the gauge itself. Now sometimes these gauges are tilted or rotated, so what we need to do is to de-warp the image so that we have a straight view on it. And then finally we can read the indicator. Now sometimes this works okay, but sometimes there's very high reflections or something is written on it, or they purposefully rotate it or cover it with something. So if it's not able to read it, we try from different viewpoints again, and if all of these don't work, we report back to the operator that something's wrong and the robot could not measure the state of this indicator. This is our user interface on the operator side, where we have a 3D view based on RViz showing all the important elements, and on the left and right we have a situational camera, the wide angle, and on the right the inspection camera, which is the zoom camera. One of the nice features is that we can click on the situational camera at a certain point and then have the zoom camera zoom in onto that particular element. On the lower side I show one of many modules that we have here, the mission and control and protocol. So where you see the state of the mission, how the mission progresses, and the protocol, what's been happening. All the sensors and actuators are shown here in this image, so we see every state of the robot on a lower level and can quickly see if something goes wrong. Together, if you're not looking at the consoles, any errors that might occur, we also show in the error protocol. The nice thing about this is based all on RQt plugins, so if somebody doesn't need this complexity, we can also just use the plugins, for example, to stick together a locomotion view. So if somebody's only concerned with locomotion, he can create his custom view, and here, for example, on the left-hand side, we show the gait pattern of the robot, so for a less complex interface. Now, since everything runs over wireless, and sometimes the wireless drops or is really slow, we have taken some consideration in the bandwidth. So of course we only want to transmit data which is really relevant and critical, such as the robot state and position, to the operator. And everything else is only, such as videos and maps, is only sent to the operator on demand. So it's very easy on RViz. If you click on this element, and we'll make sure that transmission happens, and it's easy to turn on and off these elements. Now, what we've noticed is when we use TF on a robot, since we have a bunch of states and a lot of joins, is that this can really saturate the bandwidth. So internally on the robot, we run a normal TF, but we created a minimal version of it with much lower frequency, called what we call here TF minimal. We transfer this over the network, and on the operator side, we just easily remap from TF minimal to TF, so we can switch between a high bandwidth and a low bandwidth network easily. So this really helped to get the bandwidth down from a couple of megabytes to a couple of kilobytes a second. We also wrote a connection status note which continuously monitors the health of the Wi-Fi and triggers kind of a recovery behavior in case the Wi-Fi is lost for too long. What's been also useful is what we created is also available is a Ubuntu menu bar which shows you kind of like the state, the ping state of each of the computers that you have on board of the robot. Also, if you have multiple robots, if you have connection to all of your robots, which is easily set up and continuously shows you if you're actually in connection with your robot. And also on the user side, when we navigate in this complex environment, what we've been doing is to create a pose graph, and here you see how we manually, in ARGOS, create this pose graph. So the user defines certain positions and rotations of the robot and defines, okay, how are these two poses connected, with what gate, and if all the inspection elements, of course, are in there, and if certain actions, kind of like a stair climbing maneuver needs to be done, etc., it's triggered and stored in the pose graph. It's easily debuggable since it's in ARGOS, and the nice thing is once we have this pose graph, we can use this online when running missions to update it. So in case the hallway is blocked, we mark it in the pose graph and the robot can find an alternative route to complete its mission. On the mission side, there's a lot of reasoning going on. For example, if there are certain tasks, or if the gauge is above 2 bar, do this. If it's below, then measure also this type. So there's a lot of logic going on. What I've been doing is create a C++ library, which is very similar to Smash. The entire missions are defined in a YAML format, so it's very easy for the user to edit and read. And we have also created kind of like common building blocks for this challenge to facilitate the construction, which means a typical mission from scratch we can create between 5 and 20 minutes. And one thing that I've been working on is called the ARGOS multiplot plugin, which is a little bit an alternative to the existing plotting tools which are based on Python. Our version runs on C++, is very efficient, and of course you can plot multiple views in one window. It's very easy to edit, save, and load different configurations. You can either just live plot your variables, or the nice thing is if you have a ROS bag, you can load that directly into multiplot and then render it at once. Like I said, it's very easy to set up, and how we support this is through this tool, the variant topic tools, which is also available open source, where we can parse the message structure and read the content of any ROS message. So you can click together your plotting tool very easily. Also, the X and Y axis are freely choosable, so what you can do is also put positions on the Y axis, such as in this example where we plot the feet positions and the base of the robot as it climbs up a step. Now, I have been talking about these elements, the locomotion PC, navigation, inspection, and the operator. In this last part, I'd like to talk about how we have been keeping this complexity and how we try to keep things smooth. One of the things that was important for us is to keep the same setup on the developer's PC and also on the robot. So what we're using is Ubuntu 14.04 long-term support and ROS Indigo. Of course, we're heavy users of Git, where we use Bitbucket and GitHub. And for consistency reasons is we agreed, so we wrote kind of like a wiki page, which is also compatible with most of the existing ROS packages out there, which kind of like puts conventions on how we structure packages, how we do the formatting, the naming, code style, etc., which is also available. We make extensive use of simulation. So all our sensors, the laser, all the environment is completely modeled in Gazebo, and we can also run, for example, the state estimator inside, and we can like play around with the complexity of the simulation that we want to achieve. And since locomotion with this robot is very complex, we have been trying to visualize as much as we can in ARGOS. For example, here you see the robot walking, you see the support polygons, the center of mass, center of pressure, and how the friction cones open and close, etc. So this really helps to analyze and debug the complexity of this walking robot. The nice thing if you use ARGOS is that it goes for simulation, which is important, but also we can do the exact same thing on the real robot. And if we cause disturbance, etc., you see this everything live in ARGOS or from a ROS bag. If you have hardware, it's important to do lots of tests, and what we have been doing, a little bit inspired by HMC, is to do weekly shakeouts on the robot where we run through a sequence of defined tasks every Friday. The problem is often we're very busy and don't do this, so one of the tricks is to have lots of demos where if the demo is somewhat interesting, is somewhat complex, you can measure the state of your robot just by running through these demos, and you make sure you maintain the high quality and the functionality even if the software updates. Of course, we do continuous integration. We took a while to set up a complete Jenkins server for all of our packages. Most of our packages are somewhat unit tested, and what we're actually really happy about are these ROS integration tests. We run these every night where the robot goes through a bunch of sequences, like here, kind of like demo motions to check if everything still runs fine. It's important to not always start at 0, so we randomize also the position and yaw angle of the robot. So here the robot is dropped at random position and needs just to walk forward. So anything that the user forgot to test in rotation, or problems with that, is automatically captured at night. So far we have concentrated on the locomotion of the robot. In the future I'd really like to include the entire mission of ARGOS, so that every night we run a complete ARGOS mission together with state estimation, laser, and inspection, etc., and also the reporting back. One of the things that we started doing is to always log on our robot, since if there is an accident or something happens, you only want to have it one and want to have the data ready. And then it's very easy to get those ROS backs onto your computer and use our tools, such as RVS and ArcQt Multiplot, to really go step by step through what happens and read the data from the robot to analyze this. In conclusion, what I've shown is our work on the ARGOS challenge ANYmal, and where we showed 10 open source packages. Internally, it's much more complex. We have over 250 internal packages, also for different projects. So one of the things that we have to learn is how to deal with lots of developers, roughly 10 to 20 developers, depending on how many students we have. So this is something that we had to learn over time. 2 years ago, we had almost no ROS on our computer. Now we have the entire pipeline, so we had to make sure that we can deal with this complexity. One of the biggest issues that we find when we fight in our group is the naming. Turns out it's one of the toughest things in programming. So if somebody can tell me how to do that properly, let me know. What we try to do is to have the algorithmic part like clean C++ or Python libraries, and then use ROS as a glue. So we can easily switch the ROS version, or in the future switch to ROS 2 without major rewriting of our software. Still, Wi-Fi is very problematic to us. If everybody knows of a solution, it's one of the hardest problems that we face with in this challenge, actually. And since we have a legged robot, the problem for us is if we have a collapse or shutdown or some error, a robot would just fall, since it also dynamically runs. So for us, what we do now is really work on the reliability of a robot such that it can do tasks over hours without having any issue in our software. With that, I'd like to thank all my collaborators. Thank you for your attention. I'll be open for questions.
Hi. I actually have 3 questions, but I don't want to hog the question session, so I'll ask.
We have enough time.
Okay. So the first question is about the KinDR library or the KinDR package.
The Kinder, the rotations, yeah.
And you also spoke a little bit about dynamics or taking derivatives and stuff like that. Do you also support symbolic derivatives so we can use it for optimizations and also plug in with, say, for instance, dynamics libraries?
So dynamics, the biggest part in the library is based on rotation. There's some limited things for dynamics. We don't support any symbolic, so it's all numeric. So you need to plug in, you need to do your optimization yourself, formulate it, but then you can use expressions from this library to consistently handle your rotations.
So numerical is supported then?
So it's not an optimization tool, it's only to represent deal with rotations and translations.
Oh,
itself.
okay.
Yeah.
Okay. Second question I had was related to the OMPL RRT star that you used. And you also said about online. So do you? So what sort of cost functions are you using, and do you use some parallelization? Because RRT star does take some time.
So what we do is a split between global and local updates. And when we run these, I think in parallel, Martin, who sits here, is the author of this. The cost function is really based on the traversability map. And first we look at, so we have multiple levers. First we look at like a circular pattern, which makes it easy, rotational invariant. And if it doesn't work, then goes down to a smaller circle, and then it really looks at the footprint of the robot. So we kind of get scaled. If this planner doesn't find a solution, it goes more into complex cost functions. Which, if the environment is easy, then you have a solution very quickly. If the environment is harder, then it might take a while for you to compute,
so
to
when
update
you
the plan.
Okay, so when you say online, what are you looking at? Like how many, the time frame, for instance?
So I think the local planning is roughly updated every second, and the global every 10 or 20 seconds.
I see. Okay. And the last question was regarding the Smash similarity to the C++ similarity and with Smash. Is that also open source?
That's right now not open source.
Okay.
The reason why we did this is in Python we have been a little bit frustrated, and we run the mission. It's when you have to run through the missions first because before you get any errors. So we wrote this in C++. If there's interest, we can think of open sourcing this too.
We used the Python implementation also for Amazon Picking Challenge, and we also had to fight with it quite a lot.
Okay.
So C++ would be quite a nice contribution.
Okay, so I'll forward this to the author of this package, Remo Detail, and we'll talk about open sourcing this.
Thanks a lot.
You're welcome.
Thanks.
Thank you. What we, from the beginning on, we looked at, okay, how many dependencies do I have in my package? It's automatically, almost only a few people, actually, if you look at the developers, have the full stack of the robot with the navigation, etc. installed. So automatically, when people only concerned with motion planning, mapping, locomotion, it separates very quickly. So what we're trying to make sure that we have kind of like these common packages. That's why also the grid map, this Kinder library, etc. came up, where these are tools that we need everywhere. So we like identified those on the way, and then did that work where we thought, okay, this package has no dependencies on a project, and what we tried to do is not create a robot for the ARGOS challenge. What we tried to do is to create a general platform. Also, we have founded a company in the future to work with these robots commercially. So our goal is really to create a robot that is flexible in use. So from the beginning on, we analyzed kind of like the structure and made sure that the dependencies are somewhat sane. Still, there's a bunch of work to do. And then I think what we like about open sourcing, that the entire hosting is taken, which is awesome, by ROS on the server. So that's the part we like, really. And then internally, the stuff that we keep internally is only mostly for the reason that it's not good enough yet to open source. So in the future, we like to open source as much as we can. Also get feedback. We have gotten to a bunch of our software very good feedback and feature requests, bug reports from the community. So that's the reason how we want. And then, of course, who wants to use a package which is highly dependent on all of our other software? So that's the philosophy behind it. How can we separate these algorithmic parts? But we do it on the go. There's, there's no master plan on how we do this.
What's your power budget, and how much does it weigh?
The robot weighs, depending on what you put on top, 28 to 32 kilos. So it's always important for us to have a robot that one person can carry. So compared to the other participants in this challenge, they weigh 80 or 100 kilo robots. So for us, we want to really have a lightweight robot. The power consumption is roughly 280, 300 watts, depending on what you're doing. So it can, with its battery, you can run 3 or 4 hours. Thank you.
I'd like to reiterate Jackie's comment, like really well done software design here.
Thank you.
And in particular, I'm interested in your Wi-Fi problem of having too much data transmitted over TF and then using TF minimal to compensate for it. Do you just eliminate all fixed frames in minimal, or what is TF minimal? You could speak to that.
So the fixed frames are still there because they don't use any. If we use TF2, all the fixed frames are there. TF on the operator side essentially is only used for visualization. So it's nice if the operator sees if the legs are moving or if they're up in the air because the robot crashed. So it's not real any computation happens on the operator side. If we lose Wi-Fi, all the mission planning, etc., happens on the robot, so the robot will just continue. TF minimal is then just kind of like which each TF topic, which is high bandwidth, we create a second version, which if we don't need 400 hertz to visualize, right? So what we do is maybe run it at 10 or 5 hertz for visualization reasons. On the robot, we have a fast TF to do all the computation, so they're accurate, but for visualization purposes, we use this lower bandwidth TF minimal to show for the operator.
Cool.
Does that make sense?
Yes. Thank you.
Thanks.